Afternoon. Hello guys, good afternoon. Good afternoon. Hi. Hi guys. So hope everyone is doing great. Good afternoon guys. Yes. So hope everyone is doing great. So let me please take the polls, guys. Meanwhile, I need to set up few things. Till then, please try to take the polls. Whoever is present here. So hi everyone on YouTube Live and also everyone on. I think my network is very slow today. So there is, I don't know how far the class can happen smoothly. Network ತುಂಬಾ ಕೆಟ್ಟದಾಗ slow ಇದೆ. Okay guys, hi. Hello. So please give me some time so that I can set up everything here. So since my network is slow, I'm not going to turn on the camera guys today. Will be, yes, we'll be talking or we'll be talking over like this. Yeah, hope my YouTube live is active. Yes guys, hello. Yeah, so hi guys, I hope, yes, hi. So I'm not starting a new lesson guys today. Yes, I'm live. So I'm not starting a new lesson guys today. So we'll be discussing about since we have midsem exam already. So yes, we are starting with the crash course actually. Only the crash course today. So it's like we'll try to complete, yes. So we'll try to complete this one complete chapter. I mean this chapter and the next chapter, alternating current. Why am I doing this I'm doing because yeah, everyone might have felt this chapter, these two chapters a bit tricky, right? So and are a bit confusing too. So we'll be talking about, I mean we'll be taking these two classes today. And yeah, if you have any doubts regarding these classes, we can discuss about these two chapters doubts, and we are good to go. So if required, I'll also take up doubts of people who are, I mean I'll also take up another doubt solving session similar to this sometime later in this month before your exams, physics exams. Okay. Okay guys, great. So let's start. Yeah, everyone in Zoom, please, I hope all of you are able to hear me and see the blackboard clearly. Since my network is very bad, so I'm not turning on the camera again. Yeah, I'm notifying that. Cool, great guys. Yes. Okay. Okay. So let's begin. So we are going to talk about electromagnetic induction today. So what do you mean by, what do you know about electromagnetic induction? So what do we know about electromagnetic induction? What do we know about electromagnetic induction? So what happens actually in electromagnetic induction? Yes, I'm waiting for the answers. I'm waiting for the answer. What do you by what do you in general mean by electromagnetic induction? Okay. You guys, come on, tell me. So what is induction basically? We studied in first chapter, right? In our first chapter basics, we studied what is induction. So what is induction basically, guys? So we discussed induction. Can you tell me what is induction? What is induction? Only induction. Induction. So I'm waiting for answers from both YouTube Live as well as from students over here. Yes. Okay, so induction was a forceful charge. So you know what we studied yesterday in a stress class or day before the stress class, we studied about induction. What was happening in induction? It was a forceful conversion of charge, or forceful production of, or formation of charge on a sphere, right? If you remember, it was a forceful formation of charges on any neutral surface. Similarly, what is electromagnetic induction now then? What do you mean by electromagnetic induction? Electromagnetic induction is like in a state, in a natural state, if we induce, yes, if we induce some extra, if we by forcefully produce some electric and magnetic fields by some means, then we get the electromagnetic induction. So guys, what happens initially was, so there is a relationship between the electricity and magnetism. Since ages there is a relation between electricity and magnetism. So when did we start thinking about electricity? When did we start thinking about magnetism? So it was in the early 17th centuries or 18th century where we started to think about electricity and magnetism. Okay, so about 19th century, yeah, in the late 19th centuries or early 19th centuries, there was this guy called Oersted. There was this guy called Oersted who invented or who found out that a current carrying conductor produces magnetic field. So he discovered in around 1820s, he discovered it by accident. What happened was, he was observing conductors. So he was connecting the conductors with the battery and stuff, and he was checking, okay, will it produce magnetic field, so you might be remembering this. In your 10th standard you might have studied that experiment where you have a conductor, in which through which there is a current carrying conductor, right? So you have some paper. In this paper there is some metal filings, I mean iron filings were present. And what happened? You pass a current through this conductor. Then what happened? These conductors formed current circular loops. These conductors, or the place through the conductor, right? There was the conductor, and these iron filings formed some circular loops, if you remember from your 10th standard. So this was Oersted's experiment. So Oersted, in his experiment, he found out there is a relation between electricity and magnetism in the early 1820s. Okay, so yes, whenever a current carrying conductor is present, it generates also the magnetic field. This was observed in Oersted experiment. So what in Oersted experiment, that a magnetic needle gets deflected when current carrying conductor was placed in its proximity. Okay. Next, thus we established that moving charges produces magnetic field. Okay, so we came to a conclusion, what the moving charges produces magnetic field. Then, okay, if that is true, what about the converse? What about the converse? Sir, is the converse true? What is the converse, sir? So, sir, if a current carrying conductor can generate magnetic field, if a current carrying conductor can generate magnetic field, then can the can the magnetic field also generate current? Guys, yes, those who are asking about the first chapter, we will complete the first chapter. This is a crash course. I'm doing this class because I'm again clarifying this. I'm doing this chapter only because of your midsems. We'll come back to first chapter soon after your midsems is done. Okay, thank you. Please feel free to ask any doubts regarding this chapter. Yes, thank you. Cool. Okay. Is the converse okay? Now we were discussing about, is the converse also true? Can moving magnets produce electric current? Yes, yes. Most of you are replying yes. Thank you. Yes, yes. Even the moving magnets can produce electric current. That was in the case of a generator, right? Okay. The answer is yes. So this was discovered again by Michael Faraday. Okay, Michael Faraday, a physicist who discovered this phenomenon. So he was the first person. What he did, Michael Faraday used a U-shaped bar magnet, U-shaped horseshoe magnet. You know, there is some U-shaped horseshoe magnet. He used this magnet, and he took a current carrying conductor. He took a current carrying conductor and passed electric current through this. Now what happened? Okay, this levitated. Second, okay, this was observed initially. Later, what did Faraday do? Faraday took this horseshoe magnet and took the conductor, and instead of connecting a battery, connected a galvanometer to this. He connected a galvanometer to this. So we'll check about these now. So the Faraday initially explained the concept called magnetic flux. Okay, so when this was happening, he tried to move this conductor up and down. What he did, he tried to move this conductor up and down so that this conductor cuts the magnetic field generated by north to south pole. From north to south pole, there was some magnetic field, right? You know, you have studied in your 10th standard. From north to south pole, there exists a magnetic field, right? So when your magnetic field was cut by a conductor, what did Faraday observe? The Faraday observed some deflection in the galvanometer. Okay, to explain this deflection, he came with the idea of magnetic flux. Okay, what is magnetic flux now? So magnetic flux is something similar to electric flux. By now, most of you might have studied. If you have not studied, it's fine. Magnetic flux is nothing but measurement of amount of magnetic field passing through a given area. What is magnetic flux? Say if I have magnetic fields, so if I have some magnetic lines of forces which are passing through the given area, then the magnetic flux can be given as given by phi. Flux is equals to number of magnetic field and field lines passing through the given area. If A is the area of this, yeah, object, whichever object we take, and B is the magnetic field, then the flux passing through this area is given by phi is equals to B dot A. Which are the flux here, guys? Which is the flux? Only the magnetic field which are passing through the area is flux. So everything which are marked in yellow are just the magnetic fields. Every arrow which is marked in green are the magnetic flux. Okay. Yes. Cool. Then we come to something called as area vector. Now, why do we require area vector? So to calculate the magnetic field, we know that the idea of flux was nothing but phi is equals to B dot A. It was dot product. So for me, for my simplification of maths, I needed another vector. So I assume, or I created a vector considering area as a magnitude, the surface area as a magnitude, and the area direction was perpendicular to this area. If we take the normal direction, normal of surface area was considered as direction of area vector. Okay, so if I consider area vector is nothing but area of a vector, the area of a vector of a plane surface whose magnitude is the area of the figure. So if I have any surface area, then the magnitude will become the magnitude of the surface area. Then the direction is always perpendicular or normal. So if I have a flat surface, then anything normal to it or perpendicular to it becomes the direction of that area vector. Okay, the area vector of a plane surface whose magnitude is the area vector, the direction is perpendicular to the surface area. So when we consider area vector for simplification of maths in case of magnetic flux. Okay, so what happens if we have, okay, we got to know what happens when we have a planar surface. Now what happens if we have a curved surface? Okay, what happens if you have a curved surface? So in this case, if we have a curved surface, magnitude of the area becomes, okay, whatever the area I have in the curved surface, whatever the area I have, this becomes the magnitude. And normal to this, if I draw any arrow which is normal to this, normal to that particular area, say if this is a curved surface, if I draw a normal to this, now this normal which is acting perpendicularly outwards becomes my direction. So what happens to my area vector? My area vector is vector A. I can consider area vector as vector A. Magnitude of surface area A, and direction along A cap is here A cap. What is the direction? It's always normal or perpendicular to surface area. So if I draw a perpendicular to this surface area, that becomes my area vector's direction. Got this? Yes. Come on, guys. So yeah, I hope. Yes. Okay. Okay. So guys, yep. Come on. Area vector. If the surface is spherical, what happens if the surface is spherical? Yes, correct, Manasa Banot. Yeah. Yeah. Yes, Srishti. What happens in area vector? Okay, if the surface is spherical, what happens if the surface is spherical? Okay, my magnitude is zero. Why is my magnitude zero? And direction is perpendicular outward. So I don't have a closed. I have a closed surface here. I don't have a open surface. Right. When I have a closed surface, we apply which law, guys? When I have a closed surface, we apply which law? Tell me which law do we apply for a closed surfaces? We want to calculate the flux for closed surface. Which law would we apply? Guys, yes, Gauss's law. We apply Gauss's law. So if we apply area vector to these, we get the area vector's value as zero, magnitude as zero. By Gauss's law, we'll get the difference. So you have studied for electric field when applied for Gauss's law, the closed surface integral. The closed surface integral was nothing but q enclosed by epsilon naught for electric field. This was for electric field. Then what is for magnetic field? So for magnetic field, you have something called as Ampere's circuital law. We'll study about that. Or have you studied this already, guys? Have you studied this already? Ampere circuital law. Okay, what was Ampere circuital law? So in a closed integral of B dot dl, so the amount of magnetic field produced is directly proportional to or equal to mu naught mu times I. If you know this, click on yes if you know this. Yes, cool. Yeah, correct. Correct, guys. Yeah. Next, yeah. Next, we'll talk about, okay. So let me know about area vector. If you have understood this, I'm going to give you a question on area vector. The question is, which of these area vectors marked in the figure is or are correct? So I have area vectors A, B, C, D, E, F. Which of them are correct? So I'm not launching poll. Please answer only in the chat box because I don't have. Okay. Please answer only in the chat box, guys. Okay. Which of them are incorrect? I'm asking which of them are incorrect. Okay. I'm not asking about how many are correct. I'm asking about which of them are incorrect. Hari Prasad. I have a doubt from Hari Prasad. He says, sir, in an open or closed surface, the direction will be inward and outward. How will we know it is outward or inward? So, yes. So in a closed surface, that's the reason the magnitude is always zero. Okay. So we always consider in a closed surface, we consider only the outwards direction for area vector. Okay. To answer your question, Hari Prasad. Yeah. Okay, guys. Cool. So, yes. The answer is none. All are correct. All the directions marked are perpendicularly outward, hence all are correct. Okay. No, yes, guys. So I see most of you in YouTube as well as here are answering few parts, but I mean, all, see everything, all the arrows here, A, B, C, D, E, everything is pointing outwards, right? If you see the curved surface, if you see the curved surface, all are normal to the curved surface, so all perpendicular. Okay, all directions are perpendicular to the curved surface, so all are correct. Okay. Okay guys, so what is magnetic flux now? How can I represent magnetic flux? Mag- okay, magnetic flux is given by symbol phi. Okay, phi is directly proportional to number of field. So what is number of field? So if I have a given area, okay, if I have a given area, number of magnetic field lines passing through them gives the strength, or gives the strength of the area. Yesterday we learned in electric flux also, right? Similarly, when we have number of lines passing through them, if more number of lines are passing through the short, I mean very less area, less surface area, then we can say that, yeah, we can say that the flux is high. Can say the flux density is high when we have large number of magnetic field passing through small amount of area. Then we can say the flux passing through that area is very high, right? Then okay, what about if number of field lines on the magnitude of area is given for a given magnetic field? Then okay, okay, the number of, okay, what are the factors in which my magnetic flux depends? My magnetic flux depends on number of field lines. Okay, my magnetic flux depends on, the flux depends on number of field lines passing through it. First thing, what is the first thing? First thing, it depends on number of field lines. Okay, what is the second thing it depends on? It depends on the angle of orientation. Say if my surface area is bent to some degrees with respect to some with respect to horizontal, it is bent to some theta degrees, then what is the flux, or what is the number of magnetic field lines passing through that given area? Yes. So in that case, my flux can be given with an expression phi is equals to b dot a. What is the abbreviation? What is the dot product, guys? What is the dot product of flux in this case? Yes, yes, phi is equals to b dot a. So what are the factors my magnetic flux depends on? Okay, excuse me, phi is equals to b dot a cos theta, right? Depends like this. Yep. Then what are the things my magnetic flux depends on? My magnetic flux depends on magnetic field strength, the orientation of the magnetic orientation of the area, and the area itself. If my area is more and the magnetic field lines is more, I have more magnetic flux. If my area is less and magnetic field lines is more, even in that case I have less magnetic flux. Yes. If my angle of orientation is less, then my magnetic field is also less. Magnetic field lines passing through the area is also less. Then what can I say? The magnetic flux passing through them is also very less. So in a planar area vector A normal making an angle of theta with magnetic field B, then the magnetic flux is given by expression what? Phi is equals to BA cos theta. As we expressed before, we know phi is equals to B dot A, then phi is equals to BA cos theta. Yes, where B is a magnetic field, A is the area vector, and theta is the angle between magnetic field and area. Is the angle between magnetic field and area. Okay. So it's similar to that of electric flux, right? So in electric flux, we have not completed electric flux in our regular normal class. We'll complete that. So, but in your CBSE class, you might have studied electric flux by now. What is electric flux in that case, guys? Okay, magnetic flux is similar to that of electric flux. But what is electric flux? Can anyone say electric flux? Again, electric flux is phi E. Phi is equals to, okay, we can write electric flux as phi is equals to E dot A. Even in that case, we have derived this formula. Okay, cool. Yes. So, yeah. some concepts of electric flux. We have studied some concepts of electric flux, right? So it is similar to that of the magnetic flux. So, or I can say like this: some concepts of magnetic flux is similar to that of electric flux. Say measurement of magnetic field pass through a given area. So what does magnetic flux depends on? Similarly, like electric flux, magnetic flux also depends on measurement of magnetic field passing through the given area times area vector. So SI unit of magnetic flux is Webers. Note this: SI unit of magnetic flux is Webers. Okay. So the magnetic flux is a scalar quantity. So though I have an area vector, it's a vector cross. It's a cross. Sorry, it's a dot product. Remember, this magnetic flux phi is a dot product. When we have a dot product, guys, by maths, you might be knowing A dot B. If I have a dot product, that dot product is also called as the scalar product. If you know the dot product, whenever we have dot product, it's also called as the scalar product. So this, the magnetic flux is also a scalar quantity. It's a scalar quantity. Okay. Make note of this. In J means they may ask this question: what is the dimension of magnetic flux? Okay. Make note of this. This you need to remember. Okay. You can derive, but try to remember this. Okay. Yes. Okay. If you have understood about magnetic flux, now try to solve this question. Guys, everyone, please try to solve this question. We know we have a flat metallic plate. We have a flat metallic plate of area. What I have a flat metallic plate of area 10 meters square. Okay. It is placed in an XY plane. The magnetic field is given by B. Okay, I have magnetic field B is equals to 12 Tesla in the Z direction. It's in Z direction. Say if I consider X, Y, and Z, I have it in the Z direction. Find the magnitude of flux passing through the plate. So I have kept it in this X, Y, and Z plate. So this is yeah, my plate is like a sheet, right? Now what is the magnetic flux passing through this? What is the magnetic flux passing through this plate? Calculate, guys. Everyone try to calculate this and let me know. Calculate in your chat box and let me know. Oh god. Okay, answer is yeah, Tesla per meter square. Yes, Tejas, yes, even that's correct. Dikshita Weber's correct. Okay. So yes, it's what was the formula? Five flux 5 is equals to B dot A. So okay, we have to consider area vector in the direction of same of magnetic field in this case. Okay, so we get B dot A. So what's the answer? Okay, most of you are giving 120. Most some are giving 1200. So what's the correct answer? So area of the plate A is 10 meter square. Direction of area vector will be in the same direction as that of Z. Then magnetic field was 12 Tesla. Okay. Since my angle is 0 degree, what is my cos theta? My angle is 0 degree. So what's my cos theta? What's my cos theta value? Yes, cos 0 is 1, right? Correct. Since my cos 0 is 1, yes, so I'll get the answer as phi is equals to BA cos theta, that is 120 Webers. Guys, I know what mistake you did. So most of you saw that meter square, right? So saw this meter square and squared this. Never do that. Never do that. Most of you saw that meter square part and got confused. I hope that's your confusion. Was that your confusion? Yes. Okay, cool. Don't make that mistake. So this is just the area area is given by 10 meter square. I know magnetic flux B is 12 Tesla. Then what happens to my flux? Flux is B dot A cos theta, where B is 12, A is 10, and cos theta value cos 0. So we have 120. Cos 0 value is 1. 120 Webers. Congrats all of you, those who have given me the right answer. Yes, congrats, you have learned this flux. Yeah. Next, we come to Faraday's experiment. Okay, what was in Faraday's experiment? So Faraday tried three different experiments. The first experiment is he tried to keep a bar magnet. When he bought near, okay, he tried to keep a bar magnet near a coil stationary. So first, what did he do? He took a bar magnet, he kept the bar magnet near the coil and kept it stationary. He did not move it. So there was no current flow in the coil. Next, as the magnet moved, so there was some current start to flow in the coil. So when the magnet was moved relative to the coil, there was some current flow in the coil. Direction of current changes depending on the direction of motion of the pole. You can see in the animation. So what was happening when was trying to move in? When the magnet is trying to move in, you could see the electrons move in one direction, whereas when the magnet is trying to move in the opposite direction, the electrons also in the conductor move in the opposite direction, generating the electric field. So the direction of electric current generated depends on the direction of motion of the pole. Got it? Yes. Yes, guys. Next. So relative motion between the magnet and the coil induces a current in the coil. This was Faraday's first experiments observation. What did we observe? What did Faraday observe in this? Faraday observed that, yes, the relative motion between the coil and the magnet, or what was Faraday's law? The rate of change of magnetic flux. So the rate of change of magnetic flux linked with the coil. So we know what is flux. So this flux which was linked with the coil, which was supposed to be cut by the coil, induced some current in the coil. This was Faraday's first experiments observation. Rate of motion between the coil and the magnet induces electric current in the coil. Okay. Okay, what was second experiment? Faraday then, okay, we got, no, okay, if I have a permanent bar magnet, if I move that, I'll get a current in that. So why can't I try this? So when I have a current carrying conductor, it behaves as a magnet, which was explained in Oersted experiment, right? If I try to move this current carrying conductor near like a bar magnet, so this current carrying conductor, this current carrying loop, whatever I had, this behaved like a magnet. This behaved like a magnet. Which type of magnet is this? With dipoles. It behaved like a magnet with dipoles. Which type of, it created its own poles. Okay, which type of magnet is this? This is an electromagnet, right? This was an electromagnet which was, yeah, constructed, right? When we bought this current carrying conductor in contact or near the coil where I had connected a circuit, so this current, actually Faraday had connected a galvanometer. So what happened, a current carrying coil also induced an current in the closed loop. Okay, just like in the case of bar magnet, the relative motion of the current carrying conductor also induced EMF in the secondary coil. Okay, this was observed. Next, what was, okay, this was Faraday's second experiment. Then came Faraday's, okay, the relative motion between Faraday's second experiment conclusion was the relative motion between a current carrying coil and a closed loop induced EMF in the coil. Okay, this was Faraday's second experiment conclusion. Next, Faraday came up with third experiment. What happened? Okay, if I keep both the coils stationary, I won't move the coil, there won't be any relative motion. But what I would do, I would keep both the coils stationary, But what I would do, I would switch on and switch off. I'd switch the primary coil which induces magnetic field. I'll switch on and switch off that several times. Will this create an EMF? Okay, sir. Then, sir, why should we switch on and switch off? Why should I switch on and switch off, guys? Tell me. Why should I switch on and switch off? Why should I switch on and switch off the coil several times? Yes, to generate a change in current. So we know that the change in current, yes, Prakash Koda, correct. So when there is a change in current, this change in current generates a changing magnetic field. So for induction, for electromagnetic induction, what we require a changing magnetic field, which is to be linked according to Faraday's law. That was happening. To yeah so to achieve that, we were switching on and off. So current is induced in the closed loop when the current stops flowing the coil. Okay. Next, what is the final? What is the final conclusion? A time varying current in the coil induced. Okay, current induced EMF in the secondary coil. The time varying magnetic field or time varying current also induced some EMF in the secondary coil. So there was no requirement of relative motion between the magnet or electromagnet anymore. If we switch on and switch off, or if we try to alternate, if we try to make the current vary with time, the varying current, the time varying current creates a time varying magnetic field. Okay, a varying magnetic field. This varying magnetic field, which was linked with the coil, induces an EMF in the coil. This was observed. So this is how we generate most of our electricity today. Yes, Dikshita, correct. Okay, cool. Next. So conclusion, what did Faraday conclude? In conclusion, current is induced in conducting loops because of changing magnetic flux inside the loop. So whenever there is changing magnetic flux inside the loop, there was current which was being induced in that loop. This was Faraday's statement. So Faraday's law okay, if you want any statement, Faraday's law states that yep, Faraday's law states that the relative motion between the coil and the magnetic field linked, which is changing continuously, induces an EMF in the coil. This was Faraday's statement. And in conclusion, Faraday says that current is induced in a conducting loop because of changing magnetic flux inside the loop. So it was not possible for stationary magnetic field. It was not possible for stationary magnetic field. Yeah. So Faraday's laws of EMI, mathematically Faraday conducted an experiment and he concluded that the EMF induced in the conducting loop, the EMF, he gave a mathematical expression for that. The EMF induced in a conducting loop is equal to the negative of rate of change of magnetic flux linked with the coil. So E is given as E is equals to minus d phi by dt, where what is phi? Phi was nothing but flux is nothing but B dot A, where B is the magnetic field and A is the area vector, where the magnetic provided, right? Correct. So this equation is for one single loop. This equation is for one single loop. Okay. Now tell me guys, if I had n number of turns, in the coil, how would my equation change? How would my equation change? How would my equation E change? So for one loop, if I have E is equals to minus d phi by dt for n number of turns, what would be my what would my expression for EMF? E would be, yes, correct, minus n d phi by dt. Okay, sir. So yes, Faraday gave this expression E is equals to minus n d phi by dt. But sir, who gave this negative sign? Why is it negative? Okay, this negative sign is explained using Lenz's law. What is Lenz's law? So guys, before we go to Lenz's law, I want you guys to tell me what is inertia. If you know what is inertia, then Lenz's law is very easy. Okay, what is inertia? My question to you guys is, what is inertia? Tell me. Come on, guys. What is inertia? Tendency to oppose the motion. Yes, correct. Others. Yeah, right. So the tendency, yeah, the tendency to change, oppose the change of motion was inertia. Similarly, Lenz's law, what Lenz says is the tendency of an object to oppose, okay, its cause. Lenz's law is nothing but the tendency of an EM. Okay, what happened for generation of? Okay, let me erase this. What was happening for generation of electromotive force EMF in this coil? For generation of EMF in this coil, I required a bar magnet or an electromagnet, right? So this the magnetic field due to this, which was linked with the coil, was changing, and an EMF was induced in this. An EMF was induced in this, right? Similarly, when this is happening, what happens when this magnetic field is providing the when this bar magnet is providing the magnetic field, what happens is this circular loop, which induces current, which induces current. What does it do? It generates its own magnetic field when there is motion, or when there is magnetic, I mean when there is current flowing through the conductor. What happens? It generates its own magnetic field. This generated new magnetic field, whatever the magnetic field generated by this conductor, I'll mark with another ink. Say, yeah, I'll take blue. So this conductor, okay, this is green, huh? Fine. This conductor, which is carrying current, induces a magnetic field. It produces its own magnetic field in such a way that it opposes the magnetic field due to bar magnet. So the bar magnet was providing the magnetic field for electromagnetic induction, right? This what happens? Yep. Yes. What happens? This coil, because yeah, generated its own current due to this bar magnet. Now this current which was generated in the loop produced its own magnetic field, which opposes the magnetic field of bar magnet. So this was observed by Lenz, and he gave a Lenz's law, which states that we know that EMF is induced due to change in magnetic flux. But what about its polarity? The polarity is to be determined using Lenz's law. What happened when north pole of a bar magnet, see, observe this, whatever I explained. So when north pole of a bar magnet was being pushed towards a coil, there was magnetic flux linked with the coil. This changed. A change in magnetic flux produced some current, right? The polarity in the coil, okay, change in this polarity developed to oppose the increase in linked flux. Now what happens when this magnetic field was coming inwards? What happens? It created more magnetic flux, and yeah, it generated a current in this direction, which was going upwards. Now when the magnet was moving away, there was, okay, there was, you could see there was a production of magnetic field in the opposite direction. From which, where did that come? So change in the flux induces polarity in the coil. The polarity developed will oppose the increase in linked flux. So Lenz states that the polarity developed in the coil would increase the will oppose the increased link of flux. So yeah, this is possible if and only if the left face of the coil develops north pole. So the explanation here is like, if the coil itself generates its own magnetic field, if the coil itself generates its own magnetic field due to the current induced in it, due to the current induced in it, this opposes the initial magnetic field from the bar magnet. This was Lenz's law. So since this magnetic field which was generated by, yes, Since this magnetic field which was generated by the coil is opposing the original cause, there was a negative sign to state yes, the polarity opposes the cause. This was Lenz's law. Okay, so an induced EMF or electromotive force generates a current in a counter magnetic field that opposes the magnetic field generating the current. So the simplified form of Lenz's law states that opposing the cause, the magnetic field which generated the current in the coil was opposed by the magnetic field created by the coil. Hope you are getting this. Is there any confusion in this? Is there any confusion in this, guys? Let me know if you have any confusion or if you're clear. Yes. Yes, Kavya, correct. Oppose the cause. Is there any confusion in this? Okay, cool. Explain it once again. Okay, guys. I'll simplify it. Okay, I'll simplify it. I'll simplify it and explain. Say I have a bar magnet. Assume I have a bar magnet, not south. If let me know if this sync is not visible, I'll use yellow color. Okay, assume I had a bar magnet. Lenz's law. Assume I had a bar magnet. Now, this magnet generates magnetic field in which direction? Left to right or right to left in your screen, guys? Okay, I made a mistake. From north to south direction, right? This bar magnet generates magnetic field from north to south direction outwards, south to north inwards. So magnetic field is always a loop. Okay, magnetic field is always a loop, right? Now let's consider only the outward condition. Say in the outward direction, in outside, the magnetic field starts from north pole and ends at south pole. Okay, now if I have a loop, if I have a closed loop, I'll consider a closed loop which is connected to a galvanometer. Okay, now when this magnet moves in this direction, what happens? It generates an EMF. It generates an EMF. It generates an EMF. In which direction? It generates an EMF. So according to, if north pole is going, see, you can see here, okay, there is a shortcut which was also given in your textbook. If north pole is entering, the current will be which side? Anti-clockwise. Okay, the current generated would be anti-clockwise. Okay, so if the, okay, now what happens when this coil is entering, when this bar magnet is entering the coil, it generates a current in the anti-clockwise direction. How did we conclude it is anti-clockwise? How did we conclude it's anti-clockwise? So if you consider the right hand thumb rule, consider the right hand thumb rule, guys. You know what is right hand thumb rule? When we hold a current carrying conductor in the right hand, so if I have a conductor, if I hold it in my right hand, okay, the thumb will show what? My thumb will show the direction of current, and the magnetic field shows the direction, the finger sensor link shows the direction of magnetic field, right? This shows current. If I is the current, so similarly, if you consider the right hand thumb rule here, if you consider right hand thumb rule here, if I hold this with a coil, so if my thumb shows the direction of current which is going downwards, then my magnetic field will show towards this, right? My magnetic field is acting in this direction. So what Lenz's law states is, so the current induced in the loop, the current induced in the loop due to the magnetic field is in such a way that it opposes the magnetic field which is causing it. Which means the magnetic field produced by the coil, magnetic field produced by the coil is in such a way that it opposes the magnetic field from the bar magnet. See, the bar magnet is giving magnetic field from left to right, if you see, but the magnetic field from the coil is from right to left. That way we can assume, we can find, yes, then that way we can find the direction of current. Why Lenz's law was used was to find the direction of current. Okay, if some yes, I hope I have answered your question, whoever asked this. Okay, so similarly, okay, let's have a question for in that case then. The magnetic flux linked with the coil changes with 12 into 10 power minus 3 Weber to 6 into 10 power minus 3 Weber in 0.01 second. Calculate the induced EMF. Okay, guys, do this. Calculate the induced EMF. Guys, hope you are doing it. Okay, hope everyone have found the answer. Yes, have started to receive the answers. Cool, guys. Come on. Okay, someone is telling 60 volts. Others. Okay, how to calculate this, guys? Even also you have to mention the direction, not only the magnitude. Please also mention the direction. Please also mention the direction, not only the magnitude. So how do you mention the direction? Give it the sign in it to, okay, give sign to that. If it's positive, write plus and the magnitude. If it's negative, write minus and the magnitude. Okay, cool. Even clockwise and anti-clockwise also would do. Okay, so Dikshita, right? Yes, Dikshita, right? Tejas, Bindushri, right? Srishti, right? Okay, let's check. The answer is, change in flux. Guys, what's happening? My flux is decreasing. See, it started from 12 into 10 power minus 3 and ended at 6 into 10 power minus 3. So my flux is decreasing continuously, right? So my final flux was this. My initial flux was this. So what I should do? I should do the final minus initial. 6 into 10 power minus 3 Webers minus, yes, 12 into 10 power minus 3 Webers. That is 6. So minus 6 into 10 power minus 3 Webers. Again, guys, I had time t as 0.01 seconds. Remember? dt was 0.01 seconds. So when I put in the EMF equation, E is equals to minus d phi by dt, what would I get? So I know d phi, I calculated my d phi as minus 6 into 10 power minus 3 Webers. And what is my dt? Dt is 1 into 10 power minus 2. I substituted that. So on solving, what would I get? I'll get minus 6 into 10 power minus 1, that is 0.6 volts. Okay, it's 0.6 volts. Please make corrections if someone have made any mistake anywhere. Yes. This makes okay. If you have made some mistake in your calculation, I see most of you had done as 60. So only few answered this correct. It was minus 0.6 volts. So yeah, where minus 0.6 mentions anti-clockwise direction, right? Cool. Okay, guys, next question. So solenoid by now. In your previous chapter you might have learned. So a long solenoid with 15 turns per centimeter. So how many turns per centimeter is given? N is equals to 15 turns per centimeter. You have to convert it into SI. Always convert it all quantities into SI. Okay, a long solenoid with 15 turns per centimeter has a small loop area of, okay, they have given the area is 2 centimeter square. Okay, in this case what you have to always convert it into SI units, meters. So here you have to do it, guys. Yep, if okay placed inside the solenoid normal to its axis. So where is this? Okay, a long solenoid with 15 turns per centimeter has a small loop area of 2 centimeters placed inside the solenoid normal to its axis. Note this, it's normal to its axis. So what is normal to its axis? If solenoid is like this, if this is the axis, normal to the axis means here I have something like this. Okay, and carried by, okay, if the current, okay, this is something like this. If the current, if the current carried by the solenoid changes steadily from what is given, my current change, my di by dt is given, change is given by 2 is given as 2.0 amperes to 4.0 amperes in 1 second. What is the induced emf in the loop? So guys, in your previous chapter you have studied b is equals to mu naught times n into I. Please use this formula. In our previous chapter of magnetic field or magnetic effects of electric current, we had studied b is equals to mu naught times ni. What is mu naught, guys? Value of mu naught, mu naught was a constant, 4 pi into 10 power minus 7. So that's the value of mu naught. Then if you know, calculate the value of induced emf. Come on guys, what is given in this question? You have given with I, di by dt is given, you have to find dB by dt so that you could find d phi by dt. Okay, hope everyone is doing it. Everyone is doing. Yes, come on guys, I'm waiting for answers from everywhere. Okay, let us take 2 minutes time to solve this. Okay, let's take 2 minutes time to solve this, and yeah, let's complete that. So do you feel this chapter is easy or difficult, guys? If you feel this chapter is easy, and if you have any doubts in particular to ask me, you could ask. I chose this chapter based on the students' feedback which I got from few schools. So most of the schools did not discuss this chapter so well. So I chose this chapter to be discussed. Okay. So I'm waiting for answers. Come on, guys. You could try. You could try the answers if possible. Yeah. If you were able to solve this, it's great. Otherwise, it's fine. We'll solve that. Nisarga, what did you calculate? Okay. Excuse me. So I'm asking for the induced EMF in the loop, guys. I'm asking for induced EMF in the loop. Please try to find induced EMF. Okay, so yeah, we'll start then. Okay, someone have sent me 7.5 into 10 power minus 6 volts. Okay, let's check. So what was my change in current? So I had to convert my number of turns from 15 turns per centimeters to SI unit. In SI unit, it's like, yes, 15 turns per centimeter. 15 turns per centimeter is 10 power minus 2 meters. So if I do that, if I do the math, it's 15 10 per 2 per meters, turns per meters. 15 into 10 per 2 turns per meters, that is 1500 turns per meter. Okay, then change in current is given by di, 4 amperes minus 2 amperes, that is 2 amperes. So time taken dt is 0.01, sorry, 0.1 seconds. Then what is my emf e? Emf e is equals to minus d phi by dt. So what is my flux, guys? What is flux? Phi is equals to B dot A. Now, sir, what is A, sir? I said it's a solenoid. What would be its area? What would be its area? Reply in chat, guys. On if I have a loop, what would be its area? Yes, Tejas, correct. Mega, please check your answer. I asked what will be the area of solenoid. Don't give me the answer. I asked the general expression for solenoid, area of solenoid. General expression for area of solenoid, guys. I asked. I did not ask for the actual answer. I asked for general expression. Yes. Excuse me. Okay. So the flux is phi is equals to B dot A, where B is mu naught Ni or mu Ni, and E is equals to minus d phi by dt. So it's minus d by dt of mu Nia. So now what is E? E is equals to minus A times. So what is changing here? Only my current is changing. Area is constant. Number of turns is constant. Mu naught is also constant. So all of these are constant, right? So what is only changing? Only my current was changing. It was changing from 2 amperes to 4 amperes. So my change in current di by dt was calculated initially. It was 2 amperes. Now, if I put everything here, okay. So yes, correct. So whoever answered area as 2 into 10 per minus 4, it's correct. Okay. So I'll get the answer as minus 7.5 into 10 per minus 6. So Rajdash, Tejas, you missed with some power, I guess. So only 2-3 students were able to give this. If let me know if you have solved this now. Excuse me. Yes. Yep. Okay, done, guys. Understood this. Okay. Now these are the different applications of Faraday's law which we see. So I hope this you might have seen in your malls or shopping malls. They use this to detect if you have any metal conductors or metal parts with you. Say bomb detections. Also in induction furnace. So this is the induction stove which we use. Then this is like the induction pen, like whatever the writing pad we use, right? It's similar to this. So what happened here is we have a pen, the stylus. This stylus is having some coil. It is having a induction coil. Inside this there will be a resonance coil. We'll be learning about resonance soon, guys. In your AC chapter you'll be learning about resonance. So yeah, in resonance it will be resonating with the coil frequency which is being inside this tab. Okay, that's the way it experiences whenever we touch any particular point, say here or any particular point. Each has its own frequency or its own um, numbers, actually the coded numbers. So whenever we touch this, actually these are divided into several arrays, computer students know what arrays. It's divided like rows and columns. So whenever we touch a particular point, that particular point's frequency gets enacted and it's being sent to the computer. That's how these works under resonance. Okay. So even Faraday's application is Faraday gave this, right, electromagnetic induction. It's because of this induction which the resonance happen and we get to sense. Okay, the transformers which we use in our day-to-day life is also an application of Faraday's law. Okay, now what happens when the EMF? What happens when? Now let's come to actual Faraday's law. What happens when magnetic when current carrying conductor is used. Yeah, yes, correct. So when a current carrying conductor is placed in a magnetic field, so what happens in that case? So what happens? So we'll be discussing about several cases. One such case where you get problem is problems in your exam CBSE or JEE means is this. Say I have a magnetic field which is into the plane of board. Now I have a conductor which is moving with some velocity v. Okay, I have a conductor which is moving with some velocity v. Now what is the EMF generated in such cases? Hope you might have solved problems on this. Yes. Okay, we'll learn about that. So consider a conducting loop of side length L. Say if I have a conducting loop of side length L allowed to move in a uniform and time independent magnetic field. What does time independent magnetic field means? It's a constant magnetic field. Okay. So this magnetic field is constant. The magnetic field is constant means the magnitude of magnetic field does not change. It's a constant magnetic field. Okay. Now when I pass a conducting loop of side length L, say if I have a conducting loop of side length L and it is allowed to move in a uniform magnetic field then with velocity v, then we know that the flux cut by the loop is given by phi is equals to b into L into x. Now guys, if you remember what was the force, if you remember from your third chapter, or fourth chapter, magnetism, magnetic effect of electric current, what was the force experienced? Say, if I'm doing the reverse case, say if I have a magnetic field and I have passed some current through the conductor, then with what force will my conductor? What is the force will my conductor experience? So if you remember this, it would be great for me to explain. What is F? F is equals to, guys, what was the value of F? Yes, correct. Force experienced was F is equals to BB. Yeah, yes. Bigna, your answer is for cyclotron, I guess. Oh, no. Sorry. It is the right answer. Sorry. F is equals to Q into V cross P. Correct. So it was F is equals to Q times V cross B. One more was for a current carrying conductor. It was F is equal to BIL sin theta. So in both cases, yes, that was used. If you remember that, that's great. Then flux phi is equals to B into L into X. That is given by if my flux is given by phi is equals to B into L into X. What is L into X? Here L into X will be my area A. Then what happens? Applying Faraday's law, I'll get E is equals to minus d phi by dt. So my flux as E is equals to minus d by dt of BLX, B into L into X. Get, okay, what is my varying factor here? Only my coil is moving. My magnetic field is constant. Length of the loop is constant. But my coil is moving with respect to time. It's moving with some velocity. What is dx by dt? It's nothing but my velocity. Then the EMF induced is given by E is equals to B into L into V. Remember this, guys. This is very important relation. Electromotive force EMF induced in the coil in a loop which is moving with velocity v in a magnetic field, in a constant magnetic field, is given by E is equals to B into L into V, BLV. Guys, remember this? Yep. So yeah, I would like to give you a question. So okay, here is my question. I if I is equals to 2 amperes, if I is equals to 2 amperes and B is equals to 10 Tesla, okay, B is equals to 10 Tesla, moving with velocity V is equals to 5 meters per second. What is its EMF induced? What is the EMF induced, guys? Let me know. Let me know in the chat box. What is the EMF induced? Yes. Okay, I'm waiting for answers. Hello. Yes, guys. So, yeah, the answer is yes. Just substitute this. Length, we know length is okay. Length is, take it as 1 meter. Length is 1 meter. Now find the EMF. E is equals to, we know what is E. E is equals to B into L into V. So that is given by B is 10 Tesla into length is 1 meter into V is 5 meters per second. That is 50 volts. In that case, we would get, yes, right, correct. We would get 50 volts. Yes. So this is what we learned when we have an conductor moving in a constant electric field, constant magnetic field. What happens? So if I keep, so alternatively, any charge in a conductor experiences a Lorentz force equal to Q into V cross B. So this was given by you guys. I mean, Vigna, you gave this answer. So if I have a charge moving with velocity V, then the force experienced by it is given by F is equals to Q into V cross B. So that's the Lorentz force which is being experienced. Then it's given by work done in moving the charge for distance, for L distances. W is equals to Q into V into L into B. Okay. So EMF in the work done. Say you might get a question like this, guys. Okay, I'll first complete this. EMF in the work done per unit charge is given by E is equals to W by Q. That is E is equals to Q into V into B into L by Q. That is E is equals to BLV. Say you will be you might have seen problems like this. Say you have a conductor and you have another conductor which is movable, but it's connected with a resistor. Okay, assume you have a conductor. Yeah. Okay, now I have this conductor in this arrangement placed in a uniform magnetic field B, and it has a resistor of resistance R. Now this conductor is moving with some velocity V, which is of length L is equals to say 1 meter, B is equals to 10 Tesla, and again moving with velocity V is equals to 5 volts. In this case, what will be my EMF or power lost? What will be my voltage across this resistor? What will be the voltage across this resistor? Oh God. What is the voltage across this resistor? Yes, again it's 50 volts. So E is equals to B into L into V, where V is velocity, sorry, V is velocity in meters per second, we get 50 volts. Okay. So these aspect that a stationary conductor subject to a time varying magnetic field shows same results. So you have studied Lorentz force in your second or third chapter. Okay. Next, power required to push conductor with velocity V. Suppose if I have a resistance, yes, that's what. If I have a resistance of conductor R, if the resistance of the conductor is R, then what is the power required to push that conductor? Suppose, yep. Then the current flowing through that conductor will be I is equals to E by R, where E in the previous section we derived as E is equals to B into L into V. So I is equals to BLV by R. Now, force experienced by conductor is given by, no, F is equals to BL sin theta, right? Sin theta. Here, if you see, observe, the magnetic field is into the plane of board. Magnetic field is into the plane of board, and this object is moving in this direction. So if you see, it's into the plane of board and it's in this direction. So if I want to draw this, I can show like this. It's into the plane of board and it's moving in this direction. The angle between them is 90 degree. So what is if force experienced. F is, we know F is equals to BIL sine theta. Here theta is 90 degree, so I'll get F is equals to BIL, right? I'll substitute that. I know from here I, the value of I is BLV by R. So substituting this, I'll get F is equals to BIL. Substituting this in the value of I in this, I'll get F is equals to I into L into B, that is B square L square V by R. From here, I can find the value of power required to push the conductor, that is P is equals to I square R. Now, power required is P is equals to I square times R. So, okay, no, not this is not the equation. Okay, power, okay, the power required to push the conductor is given by P is equals to F into V, that is B square I L square V by R into V. So I'll get the power as B square L square V square divided by R. Okay, yes, remember this. So they would ask question based on this, power required to push a conductor. So as I mentioned earlier, there would be a current carrying conductor here and some resistor like this, and if this is moving with some velocity V, then in the presence of uniform magnetic field, what would be the power required to push this conductor, or what is the work done in pushing this conductor? Such questions would be asked. Okay, okay guys, so it's, I think, yep. So let us stop here. So let's discuss if you have any doubts in general. Let us discuss if you have any doubts in general. You could ask if you have any doubts. Yes, guys, come on. I'm waiting. If you have any doubts, you could ask in general. Okay, you want AC. Okay, how many want alternating current chapter to be taught? So one of the student is asking, sir, can you teach AC chapter tomorrow? Yes, if everyone is available, and if there is like, if you request on I don't know if we are about to supposed to teach tomorrow or not. So tomorrow you don't have physics class, so we could try to discuss and schedule time somewhere other than tomorrow, because there is no schedule for tomorrow for physics, right? So there is no schedule for tomorrow for physics. We need to find a schedule for physics. So Monday onwards, I guess your midsems are going to start. So before that, say you could choose, you could inform us on Sunday or Saturday evening or sometime. I should inquire with my manager first. Once I should inquire with him and I'll let you know. Okay. So how many would require AC chapter to be taught? How many would require AC chapter to be taught again? If you could give me a number, I could process that. I could ask that. Please click on S if you want AC chapter to be taught again. Yes. So quite many. Okay. So do you find alternating current chapter difficult? I can try to quickly cover up that alternating current chapter on Sunday. Or yeah, anyway, I'll keep you updated, guys. I'll keep you updated in the Telegram groups and the WhatsApp groups which you have. I'll inquire with the manager if he's willing. Yeah, he would always give. But if you guys want, yeah, I could take a crash course on alternating current. Okay, guys. Yes. Okay, then when can we schedule that? If yes, when can we schedule that? You should give me time. At what time should I schedule? I don't know when I could do something like that. Okay, I don't know if this is possible. I don't know if this is possible or not. I can't commit until I get permission. So I'll inquire with my team if I can conduct class. Okay, but it's not 100% sure. Okay. So anyway, I'll inquire and let you know in your respective WhatsApp groups and in your Telegram groups, guys. If there is such a class, I'll keep it informed. Okay, I'll keep it informed to you guys. So any doubts? Any more doubts? So we have 10 more minutes. So guys, for tomorrow's, okay, when is your physics test? When is your physics exam for midsem? Can I know when is your physics exam for midsem? Okay, it's the last 15th, so we have quite an hour. So we have lots of time to discuss that. Cool. Okay, we'll check that. We'll check what are the possibilities and we'll get back to you. So any more doubts, guys? Okay, 3 days gap. Okay. Okay, cool, guys. So great. So yeah, AC chapter. So I'll give you, okay, quickly I'll try to give you what's in brief what you have to study in AC chapter. So in AC chapter, guys, you have to learn about generator first, then the transformers, then power factor of I mean the transformation factor of transformer, the K, N2 by N1 is equals to E2 by E1, that one. And again there is something like the equations which you have learned, say the general formula for representation of AC wave, V is equals to V naught sin omega t, and about the calculations part, the average current part, the RMS current part, or RMS and average values of any given quantity can be calculated. So yeah, we'll discuss about this with our team and let you know the timings. So we'll discuss all of this. So I'll quickly give you a big brief schedule. I mean, we'll have a class of 1 hour or 1.5 hour, and I'll quickly try to brief entire AC chapter within short duration of time. Okay, if that is possible. I mean, again, I can't commit to this. I should get permission from my authorities, and if I get, yeah, then it's done. Okay, guys, cool. Then see you guys on. I don't know when we are going to meet again. There is no class tomorrow, and it would end. We would meet after only after your midterms, or if everything permits, we would meet early for next class. Otherwise, we would meet only after your midterms. Okay, guys. Till then, see you. Take care. Bye bye. All the best for your midterms.